Welcome to this tutorial on retrieving the gamma factor of special relativity, and we start with a transparent spaceship which is represented by this gray rectangle. And in this transparent spaceship we can look at the inside and see there is one person, and from the hair we know this has to be Einstein. And he's experimenting with time. So he builds a clock which is simple but ingenious. He has a mirror at the bottom, a mirror at the top, and with a torch he sends a ray of light. And knowing that the spaceship has a height of L equal 300 meters, we can compute the time the speed of light needs from bottom to top. So velocity is straight over time, the speed is straight over time, and therefore if we interchange these two variables, time is equal straight over velocity, and in our case straight is the height of the ship and velocity, the speed, is equal to the speed of light. If we put numbers into it, we have L equal 3 times 10 to the 2 meters, 300 meters, and the speed of light is 3 times 10 to the 8 meter per second. This cancels out, this is a 6, this cancels also out, and we get that the time needed for the ray of light to travel from bottom to top is 1/1,000,000 of a second. Okay, now let's take a look at the ship which is in movement, and this ship has a speed v, and in our example we will use v equal 5/9 of c, so it is quite a big speed. And the spaceship moving to the right, if we are outside of the spaceship we will observe that the ray of light moves not upwards like Einstein observes it, but we will see that it has a diagonal movement. And normally in the Galilei relativity before Einstein we would think that this speed, diagonal speed, is a vector sum of the horizontal component, the spaceship speed, plus the vertical speed of light, and to sum them up we use Pythagoras and we take the square root of it. But as the Michelson-Morley showed, this is not true for high velocities close to the speed of light. What happens is that the speed of light stays constant, so we don't need to take in account that the spaceship is moving. The speed of light doesn't sum up with other velocities, with other speeds. It doesn't sum up with this spaceship component, and stays constant at c. C is constant in the universe. And what this means is that we will then, if c is constant, it will be less than this sum of the two components, and therefore our observer outside of the spaceship will measure another time for the needed for the ray of light to travel from bottom to top, and this time we will call it t dash. And now we put together an equation to compute this t dash, and the equation is built around this triangle, so we are using Pythagoras, and here I already created the starting point. So we sum the two sides of the triangle, we square them, and we get the hypotenuse of the triangle. So v t dash squared plus L squared is equal to the hypotenuse ct dash squared. We then move this part of the equation to the right and write L squared is equal to v t dash squared, sorry, c t dash squared minus v t dash squared. So this is moved to this side. Then we move the squared inside the parentheses and write c squared t dash squared minus v squared t dash squared. We put in evidence t dash squared and write L squared equal c squared minus v squared times t dash squared. We then write that t dash squared is equal L squared over c squared minus v squared. And this next step, we take the square root of it, so that we get that t dash is equal to the square root of L squared c squared minus v squared. And then we can take L squared of the equation. T dash is equal to L times 1 over c squared minus v squared. And now we do something which is not clear, so it's a bit counterintuitive, but we will put in evidence this c squared. And we write that this is equals to L times 1 over c squared 1 minus v squared over c squared, which is still c squared minus v squared over c squared. C squared cancels out and we get this. But now we can take this out of the square root and we get this impressive result, L over c square root of 1 over 1 minus v squared over c squared. And this L over c, we already encountered it before. If we look at the top, this was the time measured by Einstein in the inside, and our observer outside, he measures something different, which is what Einstein measures. This is the time measured by Einstein times another factor which is called the gamma factor. Here is the gamma factor. So we get that the time measured by an observer outside is the time measured by Einstein inside of the spaceship times this particular gamma factor. If we now choose numbers, so if we choose for the speed of the spaceship as set 5/9 of the speed of light, and we had already before that Einstein was measuring 1 millionth of a second as the time to travel. If you put the numbers inside the equation here, you will get that I have to keep the video short, so I already pre-computed it. T dash is equal to T times the gamma factor, which for V equal 5/9 of C will be about 1.202, meaning that the time, this 1 millionth of second, will become 1.202 millionths of second. So the observer outside will see the same movement, which for Einstein was taking 1 millionth of second. It will see it as it would take 1.202 millionths of second. And in general, the observer outside the ship will see Einstein as it moves slower. Any movement of Einstein will look like in slow motion. So imagine Einstein while cleaning his teeth, he will move about 1/5 slower, 20% slower than Einstein himself is doing. And this slowliness is something real, so the observer outside is really something which is real for the observer outside. So time is not constant, the flow of time is not constant. The only thing which is constant in the universe is the speed of light. Thank you for watching this video.